Well, we are ready to track objects in three-dimensional space, and vector-valued functions, respectively parametric equations, which are two sides of the same coin, are exactly the tool to do that. And so in this presentation, we're going to talk about these objects, and the main goal really is to firmly establish the visualizations for these kinds of entities. We'll be a bit short on computations here, actually, which may not be that bad. But we're going to have a lot of visualizations, a lot of animations, a lot of talking about the meaning of these curves. So let's see what we're up against here. The underlying definition for this presentation is very simple. A vector-valued function c of t is a function that maps each t in its domain to a vector c of t. The crucial thing, however, is already shown in this image that is credited to the European Space Agency, and that is this input parameter t is typically interpreted as time, and then the output c of t is typically interpreted as the position vector of an object. And so basically that means as soon as you have established a coordinate system in which you can write your vectors, you can track, for example, satellites as in these images, as in this image. And so that means these vector-valued functions basically can be used to track the position of any object, be it satellites in outer space, be it motion on the surface of the Earth. And yeah, that's about it, right? I mean, there's outer space, there's the surface of the Earth, there's the inside of the Earth, but that pretty much describes everything. So, vector-valued functions can be used to describe any kind of motion as long as we can encode it all right. And so that is what we're going to start with. Let's take a look at some motions that we will revisit later on. There is, for example, the drawing of an ellipse, and we can see here that a vector-valued function basically at every time just gives you a position. So the vector-valued function really is a movie. The vector-valued function just traces this particle. Typically, however, what we want to have is we want to have a curve, we want the particle to leave a trace behind, and so typically when we talk about vector-valued functions or parametric curves, we typically will look at this trace also, and this trace is very similar to the exhaust that is left behind by a jet engine. Certainly we can do this in 2 dimensions as well as in 3 dimensions, and so in 3 dimensions, of course, the drawing gets a little bit more complicated because we need perspective and a 3rd dimension, but other than that, the vector-valued function still just tells us the position of this particle at time t, and what we're typically tracing is actually the trace that that particle leaves behind, and we're going to formally define that in just a minute, but what we typically see drawn is actually the whole trajectory. If we're looking at expressing these functions, well, again, I want us to think of vector-valued functions in arbitrary dimensions, but of course in 2 dimensions, c of t is just x of t, y of t, which is x of t I plus y of t j, which is also sometimes left angle x of t, y of t right angle. So these are the various ways in which these functions can be expressed in 2 dimensions. And in 3 dimensions, it's the same story, only that we have 3 coordinates, x of t, y of t, z of t, x of t I, y of t j, z of t k, or also in the angle notation, x of t, y of t, and z of t with the brackets around them. And so that also means that parametric equations are just a different side of the same coin, namely, it is very easy to translate back and forth between c of t being x of t, y of t, and a set of equations x of t equals whatever x of t is, and y of t equals whatever y of t is, which is another way in which vector-valued functions are often presented, and in that case people talk about these things as the parametric equations. And certainly we can also do that with a set of 3 parametric equations, in which case we would have a vector-valued function in 3-dimensional space. Okay, so for the vector-valued function, as we already have indicated, the set of all points for which there is a t, so that c of t is the position vector of the point P, that's the function's curve, space curve, or trajectory. So that is what I also mentioned before, and this image is credited to, I found it on a NASA site, and it's also credited to Jet Propulsion Laboratory, University of California at San Diego. And well, basically, these are just the contrails or the exhaust trails of jet airplanes, right? That is something that we probably have seen in the sky already. Here we've got a whole bunch of these contrails. And so we have a very, well, natural in modern day phenomenon that pretty much traces the trajectory of an object for us, which is the exhaust trail of a jet airplane that you can see in the sky every so often. And so these trajectories are exactly what we're getting when we are drawing the elliptic path, right? So now that we're talking about the trajectory, we're talking about the right side of the animation, because on the right side we are actually drawing the trajectory, we're drawing the trail that the particle leaves behind as it follows the path that is described by the vector valued function. That can also be done in 3 dimensions, certainly. The vector valued function remains this movie that just traces a particle over time. However, the trajectory tells us a lot more about how the particle behaves because it draws the whole path. Okay, so how do we get the trajectory? Well, we're drawing our usual XYZ right-handed coordinate system. The trajectory is a curve inside this coordinate system, right? And basically it is what we get if we plot the position at time t equals 0, at time t equals 1, t equals 2, t equals 3, t equals 4, t equals 5, and ultimately t equals 6 is this arrow here. So basically a trajectory is just obtained by plotting points. However, we need to be careful. The vector valued function also encodes the velocity information, the time information, whereas the trajectory could have been drawn in the same XYZ right-handed coordinate system, this is the same curve here, by something that moves a bit faster, where maybe your time parameter is now called u, and u equals 0 is here, and where previously we had t equals 1, we now have u equals 1/2, u equals 1 is where t was 2, u equals 3/2 is where t was 3, and u equals 2 is where t was 4, u equals 5/2 is where t was 5, and u equals 3 is where t was 6. So basically we can go through the same trajectory at different speeds. That kind of reparametrization, that kind of resetting of the clock, that kind of changing speed will ultimately be very valuable to us as we analyze motion in space and as we are analyzing the forces that act on objects in space. Right now it is just something that we need to keep in mind. So when we draw curves, and now we're going to talk about 2-dimensional curves for a while, of course plotting points is always an option, but it is best done with a computer. What you want to do with your mind is you want to visualize what the object looks like, and you want to use a computer to then verify what the curve looks like. And we're ultimately also going to see a 3-dimensional curve here, where I'm simply going to say, look, this is what computers are for. So as an example, take a look at the trajectory of the function c of t equals t and t squared for 0 smaller equal t smaller equal 2. Now that is something that we still ought to be able to visualize, and in fact we should, because if x is equal to t, well, then we're just going along the x-axis as if we are drawing the graph of a function f of t equals whatever t is, and so this really should just be a standard parabola. This should be y equals x squared, or y equals t squared from 0 to 2, and if we want to verify that, we can plot some points, and so certainly we could just take a couple of points that are equidistant on the interval from 0 to 2, and we realize, well, okay, if we plug in t equals 0, we get 0, 0. If we plug in t equals 1/2, we get 1/2, 1/4. Plug in t equals 1, we get 1, 1. Plug in t equals 3/2, we get 3/2 and 9/4, which is 3/2 squared. And if we plug in t equals 2, we get 2, 4. And well, then we can plot these points. And so we plot them over here in a regular xy coordinate system now, because we're looking at 2-dimensional curves now. We're going to do that for a while. Well, here, okay, here's the scale 1, 2, and 1, 2, 3, 4 on the y-axis. Here's the point 0, 0. Here's the point 1/2, 1/4, which is t equals 1/4. Here's the point 1, 1 at t equals 1. Here's the point 3/2, 9/4 at t equals, which is reached at t equals 3/2. And here's the point 2, 4, which is reached at t equals 2. The curve goes through all these points. It really is that standard parabola. and we're going through the curve from left to right, which is what this arrow indicates. We're going from the bottom up here, if you will. If we want to, however, look at the function itself, we remember the function itself has a certain trajectory, and the trajectory is that parabolic path, whereas the vector-valued function still just describes a movie. It describes the position of this particle at time t, and as we can see, as time increases, the particle starts moving faster, for example, which is the kind of dynamic consideration that we're going to have to analyze in more detail later on in this chapter, actually. Not in this presentation, but in this chapter. Okay, so when we're looking at two-dimensional curves, and when we're looking at curves in general, there are certain standard parametrizations that we want to remember because they will be useful to visualize the big picture. And so as a first proposition, if we just take a function f of x, a function of one variable, those things that we have analyzed in single variable calculus for about a year now, the trajectory of the vector-valued function c of t, where the x-coordinate is t and the y-coordinate is f of t, is exactly the graph of f as long as the domain for t is equal to the domain for x. So this means two-dimensional curves, vector-valued functions, parametric equations, if you will, those things can be used to encode everything that we have seen in single variable calculus as vector-valued functions. So what we're doing now is we are taking what we know from single variable calculus and we're embedding it into multivariable calculus, and we're going to, from here on out, whenever we're going to talk about a function f of x, we're pretty much just going to remember that a function f of x can be encoded like this, and that means we can apply everything we know about two-dimensional curves also to functions y equals f of x. Then another standard parametrization, the standard parametrization for a circle of radius r around the origin is c of t being r cosine t, r sine t. Another thing that I would recommend to memorize, even though the picture may also help. Here's our x, here's our y, we're in two dimensions, right? So here's a circle, here's a point on the circle. That would be what's described by the vector-valued function c of t, right? Because c of t just describes a point and it would travel around the circle. Well, here's the distance from the origin, which is r, which is the radius of the circle. And here, this angle, that actually is t, that is this parameter t here. And what we notice is that this is just a picture from the definition of polar coordinates. So again, even though it's something that I would recommend to memorize, it is also something that is connected to something that we have already discussed in pre-calculus. It is nothing but polar coordinates, and we don't have to look at the animation here, I hope. Again, you want to train your own visualization skills here. As t goes from 0 to 2 pi, this point is going around the circle at uniform angular speed. Okay, so the thing that I've already mentioned is now something that we can express with the circle, and that is different parametrizations can trace the same trajectory. So for example, the vector-valued function c of t being cosine t sine t, where t goes from 0 to 2 pi, traces a circle of radius 1 around the origin. Sure, we've just seen that. And that's the same trajectory that is traced by the vector-valued function d of t being cosine 2t, where t goes from 0 to pi. So what happens here is that the difference between c of t and d of t is that in d of t, our angle that is fed into the cosine and into the sine increases twice as fast, which means the input t for d of t only has to go to pi for d of t to make a full rotation around the origin. And so if we want to visualize that, well, here we go. On the left is c of t, and let's see, here's where we approximately have pi, and we can see that c of t has gone halfway around the origin. It has traced half the circle, whereas d of t from 0 to pi traces the whole thing, right? Now, of course, I let the parameter run for both, and so what we can see here, whoops, I pushed the wrong button. What we can see is that as we let this animation run, when c traces the full circle, the d traces the circle twice, which leads to the same trajectory. It's just that the circle has been traced twice. And so overall, we have the same trajectory, but the space curve on the left traces the circle once, and the space curve on the right traces the circle twice. Okay, so this is the kind of thing where, again, we want to remember that the vector valued function also includes the time information, whereas the trajectory does not. Okay, another example. Yes, okay, so here, here's where we're looking at a vector valued function c of t being cosine 3t sine 7t for t from 0 to 2 pi, and we want to sketch the trajectory. Well, this is something that will make 3 oscillations in the x direction, 7 oscillations in the y direction, so it's some kind of strange overlay. This is something where I would recommend to certainly use a computer to graph it. Patterns like these are called Lissajous figures, after a French mathematician named Lissajous. And here's what they look like. And you can see here where that the oscillations in the x and in the y direction certainly have a fairly complicated but ultimately also quite beautiful overlap. Let's stop that here at 2 pi. And these things, as I said, are called Lissajous figures. These figures actually are something that are being used in electrical engineering to measure frequencies, because basically if you have a known frequency going across and an unknown frequency going up and down, then as long as you see pictures like these, the frequencies aren't the same, because if the frequencies were the same, you would get a circle, right? And so, well, personally, I just find these figures quite beautiful, but at the same time, we also see that even though this sort of looks like a circle because the frequencies aren't the same, we certainly want to use a computer to draw these things. Whoop, and I went a little bit too slow here. And then if you actually have to analyze Lissajous figures in more detail, you can see, for example, there are 3 extrema on the left side, because the cosine makes 3 oscillations, whereas there are 1, 2, 3, 4, 5, 6, 7 extrema on the top, and that's because the sine makes 7 oscillations. That is something that I, at this stage, would not recommend to memorize. This is something where you want to just remember that these things lead to complicated patterns, and that you would want to use a computer unless your teacher tells you something else. Okay, we move on. And, well, other things that we can do with 2-dimensional curves as well as with 3-dimensional curves is we can translate between different kinds of representations. Remember this standard parametrization for functions y equals f of x, which is t f of t, translates Cartesian equations to vector-valued functions. Well, you could also feel inclined to take a vector-valued function and try to translate that into a Cartesian equation, because sometimes Cartesian equations are easier to work with, and also Cartesian equations are easier to read. So even though we don't know exactly what this thing may be, if we translate it to Cartesian equation, we should be able to recognize what this pattern is. So let's take a look at that. Well, we puzzle this thing apart, right? We take our vector-valued function and realize that the first parametric equation is x equals 2t plus 1. The second parametric, and that parametric equation can be solved for t, so we get that t is x minus 1 over 2, bring the 1 over, divide by 2. And the second parametric equation, which would just be y equals whatever this is, gives us that y is t thirds minus 1. And of course now I can plug t in for this t here, not for the 3, just for the t. And that gives us that y is x minus 1 over 2 divided by 3 minus 1. That would give us x minus 1 over 6 minus 1, and that's 1/6 x minus 7/6, because we've got negative 1/6 and negative 1 giving us negative 7/6. And of course we realize that that is a straight line. So every so often we may have a chance to recognize what a vector-valued function has as its trajectory by simply going back to by going back to Cartesian equations. That can become more complicated when we're looking at the Cartesian equation for the trajectory of the function 4 cosine t 5 sine t. And here's where we also have to be careful, because this is not a Lissajous figure. Because in a Lissajous figure, you have that your factor is in the frequencies, right? Here we have factors in the amplitudes. And so if we think of what we know about circles, well, for a circle, this was the radius factor. So if we now have two different radius factors, we ought to have a circle that has a different factor, different radius in the x and in the y direction, which means it's no longer a circle, it's an ellipse. So this ought to be an ellipse. How can we turn this into the equation of an ellipse? Well, basically, it's through pattern recognition. One thing that we always know is that sine squared t plus cosine squared t is equal to 1. That's the law of Pythagoras. Well, I need 4 cosine and 5 sine. All right, so I multiply the sine with 5, and so I get 5 sine t over 5. I still have the same object, squared. I multiply the cosine with 4 and divide by 4. I get 4 cosine t divided by 4 quantity squared, and that's still 1, right? Because the 5's cancel and the 4's cancel. Now I can pull the square into the fraction, and I get 5 sine t quantity squared divided by 5 squared, which is 25, plus 4 cosine t quantity squared divided by 4 squared, which is 16. That is still 1, and now I realize, well, 5 sine of t is y, and 4 cosine t is x. So I end up with y squared over 25 plus x squared over 16 equals 1, and that's x squared over 16 plus y squared over 25 equals 1. That is an ellipse. Okay, so that is something that we can also draw. X squared over 16 plus y squared over 25 equals 1. That would mean that the ellipse has a larger major axis in the y direction, as it is called. For an ellipse, it's called a major axis. I will probably slip every so often and just say it's the radius in the y direction. And so here's what it would look like. We would have an ellipse that is tall and narrow. Well, not that much. It is not terribly distorted from the circle yet. I've taken great care here to put the same scales on the x and on the y axis and to use square plots, and we get a circle that is a little bit squeezed. So we get an ellipse that doesn't have much eccentricity, as that is also called. And again, remember, the vector valued function itself is just the movie that traces this point, and here we're actually tracing the contrail that that point would leave behind. Okay, well, what else do we have? Yeah, one of the things, or another thing that will be important later on, is we need to figure out intersections of curves as well as of surfaces. And so if we want to find the intersection of the two-dimensional curves traced by the vector valued functions, c1 of t being t squared minus 1 and t, and c2 of t being negative 8t 3t, where t is any real number, well, I mean, we need to figure out the computation somehow, but also let's think about what these things look like. This one is t and t squared. Okay, I could just make y my input, and we would have x equals t squared minus 1, so that would be a parabola where x is the independent variable, so that's a parabola that opens to the right or to the left. Should be opening to the right here. And negative 8t 3t, well, that ought to be a straight line, because it looks awfully familiar from from the other example. And in fact, we're going to discuss straight lines in the next presentation, so this is again something that is just foreshadowing something that is to come. All right, when we want to find the intersection, we are very much used to just taking the two functions, setting them equal. We've got to be really, really careful here, because if we were to set c1 of t equals c2 of t, we would find out only the times at which the functions are in the same place. So we would find collisions between the two particles that are being traced. What we're actually interested in are the intersections of the curves. We want to know where the trajectories intersect. And of course, it could be that an intersection point is reached by c1 at time t, whereas it is reached by c2 at time s. So when we compute the intersection, really, really important here, let me flash that back and forth one more time. When we compute intersections, it is very important that when we work with parametric curves, when we work with vector valued functions, that we keep one parameter as t and call the other one s. All right, the rest, however, is just computation. So here is, I think, our first encounter with something that will become, hopefully, a happy companion to us, because the rest is really just computation. what we're getting out of this is a system of equations, right? We've got t squared minus 1t. The vector is supposed to be equal to negative 8s 3s. Well, that gives us t squared minus 1 equals negative 8s and t equals 3s. That's two equations for two variables. That is something that we ought to be able to dispatch with a computation. Now, I will say the rest is just computation quite frequently. That should not mean that I don't respect the computations, and in fact the computations can and will get quite nasty. However, the new ideas will be finished as soon as I give you that box, because the rest will be just relying on things that we have done before, and we've solved systems of equations before. Okay, this is a system of nonlinear equation, but if we know that t equals 3s, well then we're going to plug in t and solve, and so we plug in and we get 3s squared minus 1 equals negative 8s. That gives us 9s squared plus 8s minus 1 equals 0. We just brought the negative 8s over, and that one, even though I don't often have that happen in my presentations, that one actually solves. That's 9s minus 1 times s plus 1, and you can verify that by realizing that 9s times s is 9s squared, minus s plus 9s is plus 8s, and then minus 1 is up here. If you didn't see that factorization right away, I don't blame you. You are in the same boat that I am in. You are in the boat that I'm in, and that's the reason why I use the quadratic formula typically, because as factorizations, even if they are still technically possible, as those things get nasty, they're just really hard to see, and the quadratic formula would give us exactly what we need also. So if you needed the quadratic formula here, don't worry, because in the end we will use 9s minus 1 times s plus 1 equals 0 just to find where the s's are for which the thing is equal to 0, which are s equals 1/9 and s equals negative 1, and that's of course exactly what the quadratic formula would have given us too. Well, when s is 1/9, because 3s was t, we have that t equals 1/3 when s equals 1/9, and t equals negative 3 when s is equal to negative 1. And so now we can figure out c1 of t, right? Because the s was plugged into c2, so c1 of t, c1 of 1/3 will be, let's see, 1/3 squared minus 9 is negative 8/9 and 1/3. So negative 8/9 and 1/3, which is the same as c2 of 1/9, because that's negative 8/9 and 3/9, which is 1/3. And so you can see here we have an intersection of the trajectories, but the particles that are traced by the vector valued functions reach that intersection point at different times. Namely, c1 reaches it at its time 1/3, c2 reaches it at time 1/9. Similarly, c1 of negative 3 will be negative 3 squared minus 1, so 9 minus 1 is 8, and negative 3. Whereas for c2 we have to work with negative 1, and c2 of negative 1 is also negative 8 and negative 8, so 8 and 3 times negative 1, which is negative 3. So again, we have an intersection point here. So this is the double check that I will also and already have preached on quite a bit. Whenever you can double check, do it. Don't just compute the point with c1, also compute it with c2 to make sure that things really are intersection points. And well, that then means the intersection points are negative 8/9, 1/3, and 8, negative 3, and that's the solution. And if we want to visualize that, we could just plot the two functions. Here is c1. It really is a parabola that opens to the right, and we can also plot this, which really ends up being a straight line, and you would do that, of course, with a plotter that plots parametric curves. And you can see that the intersection points really are the what was it, negative 8/9 and 1/3, and 8 and negative 3. And now we're ready for the three-dimensional curves. And again, the first example of three-dimensional curves is really, again, just the reassurance that everything we've done in 2 dimensions can be embedded in 3 dimensions, because for every vector-valued function x of t, y of t, that takes values in 2-dimensional space r squared, or r2, the vector-valued function s of t, being x of t, y of t, and 0, takes values in 3-dimensional space r3 and has the same trajectory. So basically what this says is when we have in a regular xy coordinate system a curve that may look, well, rather crazy. So something that comes in from the right along a curve and from the left along just a long bent curve and from the right along an oscillation. Well, that is something that we can embed into a regular right-handed xyz coordinate system, because in an xyz coordinate system, the xy plane is still embedded, and so now this curve would just on the left come in like this, and from the right would have the same types of oscillations as we have just seen. Okay, so that means that whenever we have something that is tied to three-dimensional space, and we will have some formulas that are, if we want to apply those formulas to curves in two-dimensional space, we will automatically default back to this proposition which says, hey, if it's two-dimensional, we just stick in an artificial z coordinate and we can apply the same formula. Again, that will allow us to economize on memory a bit and talk about the concepts, talk about the ideas more, because that is what's important here. Alright, as an example, let's look at a genuinely three-dimensional coordinate. We want to trajectory, and we want to describe the trajectory of the vector valued function cosine t, sine t, and t, with t going from 0 to 20. Well, what can you do with that? Well, one of the things that you see here is you see the pattern cosine t, sine t, which is a circle in two dimensions. And so let's just split that off. That's cosine t, sine t, and 0, and then we've got 0, 0, t. All right, cosine t, sine t, 0, that's a circle that just goes round and round. And 0, 0, t, that's an upward drift, right? That stays on the axis, that stays on the z-axis. It's just that your z-coordinate increases with t. So that motion is basically the combination of a circular motion in a horizontal plane with an upward drift. So the result of that ought to be a spiral. That's something where in a face-to-face class I typically do some shadow boxing. Well, here we go, horizontal motion with an upward drift. Here's the circular motion, and the upward drift is given by the plane that is moving up. The plane signifies the 0, 0, t. The resulting trajectory is that you've got something that goes round and round and is being moved upwards, so it really is that spiral trajectory that I just mentioned. So if you wish, you could look at that and you can see this is basically a dude who's running in circles in an elevator. The elevator goes up, the guy runs in circles. The resulting trajectory is a spiral if we are tracing it in three-dimensional space. Of course, if you were in a moving coordinate system, and here we're looking at stuff that is way ahead of you in physics, for example, in a moving coordinate system, this would still be a circle, because as long as your xy plane is defined to be this moving blue plane, this thing is just circular. Now that is something that ultimately leads to things like relativity, which is way ahead in your future, but that's another thing that you could potentially think about. We're not going to mess with moving coordinate systems terribly much in this course. All right, so we move on, and we can also try to describe trajectories again. Well, we already have done that, so let's describe a different three-dimensional vector-valued function. And again, the idea is you want to see patterns, you want to puzzle things apart. So if you've got c of t being t thirds plus 1, negative 2t, and 3t, well, one of the first things you want to do is you want to take constants out. So the plus 1, that's going to give you plus 1, 0, 0. That's just going to give you a vector. And then when you've got t by itself, you can also factor that out. So this is actually just nothing else but t times 1/3 plus 1 right here. T times negative 2 in the y-coordinate, t times 3 in the z-coordinate. And so if you look at this trajectory, it is something that starts at the point 1, 0, 0, so x equals 1, y equals 0, z equals 0, and it then goes in the direction of the vector 1/3, negative 2, 3, which means it's a straight line that starts at this point and has this direction. And if we want to visualize that, okay, that animation got a little bit larger than I anticipated, but we can still see what's going on here. The blue point is t equals 0, as we are going to see if I stop it at the right time. Yeah, okay, t equals 0.01 here. That's where we're slightly beyond the point at the origin, which is technically the starting point. And of course, the trajectory is a straight line, and if you go with t from negative infinity to infinity, then you're starting to the right of the point where your r t equals 0, because remember your y coordinate, which is the one that goes across, is decreasing because we're looking at negative 2t. And, well, here is the trajectory that is being described. Your z-coordinate increases rather rapidly. Your x-coordinate comes towards you, doesn't increase that much because it goes with t-thirds. So this is something that slightly tilts towards you and to the left, if you want to put that as a three-dimensional image into your mind. Okay. Well, here's another one. Describe the curve traced by the three-dimensional vector-valued function c of t equals, oh my god, for t from 0 to 2 pi. Use a computer algebra system for something like that. Please. That's what computer algebra systems are for. And as we draw that, what we can see is, yeah, okay, after the fact, maybe we can puzzle that apart a little bit. Cosine t sine t is a circle, and it's multiplied with a 1, so the circle is preserved, but then we're going out a little bit at a very high frequency, 20t, so that is something, yeah, okay, so that's a particle that spirals around a circle. That's the kind of thing that, if not scaled like this, you can see, for example, when you have charged particles in a magnetic field, where they're probably not going to, well, I think in a circular magnetic field, which is something that you can get in an accelerator, they could technically even spiral around a circular path. But that is definitely something for which you want to use a computer. This is the kind of thing where after the fact I might be able to say something. Before the fact, before the fact I'm going to say, oh my goodness, what am I going to do here? All right. So now we're going to finish out this presentation by talking a little bit about intersections of surfaces, because if you intersect two-dimensional objects, surfaces, well, you're going to get one-dimensional objects, you're going to get curves. And so if we were to compute the intersection of the graph of z equals 9 minus x squared minus y squared and the plane x equals 1, which is a vertical plane, well, how do we compute that? Well, you've got the equation z equals 9 minus x squared minus y squared. With using x equals 1, that's just 9 minus 1 squared minus y squared. So that is z equals 8 minus y squared. X is equal to 1, and y is just y. So in order to turn that into a solution, we do what we typically do when we've got two equations for three variables. We know that one variable can vary. And so that one variable will be y. We set y equal to our parameter t for our vector-valued function. We know that x is equal to 1, and we know z of t will be 8 minus y squared, which is 8 minus t squared. And, well, what does that look like? That is the function c of t being 1, t 8 minus t squared. That looks like this. We have our paraboloid, z equals 9 minus x squared minus y squared. And, let me wait for it to come around again. That paraboloid is being intersected with a vertical plane, and the intersection is this parabola that is now standing in space. So that means it is the parabola, the intersection, the curve is actually just this space curve right here. This kind of thing is what we're going to use when we are actually graphing two-dimensional surfaces, because we're going to use exactly these kinds of intersections with vertical planes to graph two-dimensional surfaces as a bunch of these kinds of paths that you can already see as a pattern here on this blue paraboloid. Alright, but the computation wasn't that bad, right? You just took x equals 1 and you plugged it in. Well, of course, computations can become a little bit more complicated. So, for example, if I want to intersect the surface x squared plus y squared equals z squared with the surface x plus y equals 2z, even if I don't know what those things look like, and technically we don't know that yet, well, I take x squared plus y squared equals z squared. I take x plus y equals 2z. Well, I should be able to solve that for z. So z equals x plus y over 2, right? And the rest is quote-unquote just computation. And again, this one now really reiterates that this is not disrespectful towards computation or anybody who has trouble with those, because this computation will take a while. However, we know what to do, right? We know we take this z, plug it in here, get an equation x in terms of y, and that will tell us what this thing looks like. So, x squared plus y squared is x plus y over 2 quantity squared. Okay, so we multiply that out. So that's x over 2 quantity squared, which is 1/4 x squared, plus 2 times 1/2 x times 1/2 y, that's 1/2 xy, plus y over 2 quantity squared, which is 1/4 y squared, right? Nothing to it. Okay, we bring stuff over to the left side. X squared minus 1/4 y squared is 3/4 x squared. We don't have a mixed term, so minus 1/2 xy just comes over. Y squared minus 1/4 y squared is 3/4 y squared, and the right-hand side now is equal to 0. All right, now, how can we turn that into something that we can read a little bit better? It sort of looks like a circle, but certainly this part here disturbs us a little bit. And so what we can do is we can bracket things. We're going to keep the y squared by itself, and we're going to bracket the x squared with the xy term, and we pull out a 3/4. So if I pull out a 3/4 from the x squared, I just have an x squared inside the parenthesis. And if I factor a 3/4 out of a negative 1/2, I get a negative 2/3. And that's because 3/4 times 2/3, 3/4 times 2/3 is the 1/2 that we have here. All right. So now I can actually complete the square in here. I've got an x squared and an x. If I take 1/2 the 2/3 y, I end up with 1/3 y. So the term that completes the square is 1/3 y quantity squared, which would be 1/9 y squared. And so again, I simply, because this is inside parentheses, we can see now the value of adding and subtracting the same term, because I keep my 3/4, I keep the x squared, I keep the negative 2/3 xy, then I add 1/9 y squared, but I can't add 1/9 y squared on the right side because that would miss the effect of the 3/4, right? So here it is better safe than sorry. You just add and subtract the same term. We certainly keep the 3/4 y squared, and then we just multiply things out. So, okay, here's what we had on the previous panel. And now we can break that apart. This here becomes x minus 1/3 y quantity squared, and we have, of course, kept the 3/4 from out front. 3/4 times negative 1/9 ends up being, well, 3 times 1/9 is 1/3, and 1/3 times 1/4 is 1/12. So we end up with negative 1/12 y squared here, and we keep the 3/4 y squared here. And, well, all right, so now we have to add things up a little bit. This stays as it was, and yeah, 3/4 are, oh, come on, 9/12 minus 1/12 is 8/12, and 8/12 is 2/3, and we see that there's a right-hand side 0. So this still sort of looks like a circle, like an ellipse, but remember the right-hand side is 0. And the left-hand side consists of non-negative numbers. So the only way this can be 0 is if either this input is 0 or this input is 0. So either y is equal to 0, or x minus 1/3 y is equal to 0. Well, that gives us when y is equal to 0, then x is equal to 0. When x minus 1/3 y is equal to 0, well, when x minus 1/3 y is equal to 0, we still need, or yeah, this can only be 0 when both of these are satisfied. Sorry about that. This can only happen when both of these are satisfied, and so y equals 0 and x minus 1/3 y equals 0 directly leads to x equals 0, so the intersection is just a single point, and that can be visualized because, and even if you didn't remember it, even though I'd want you to remember the equation of a cone, of course z squared equals x squared plus y squared, that's a cone. For planes, we're going to talk about planes in more detail, so if you didn't recognize that as the equation of a plane, that's just something that happens right now. But we've got the intersection of a cone and a plane, and they stand in such a way that the plane actually goes exactly through the apex of the cone, which means the intersection really is a single point. Now, you probably also have heard of conic sections, which are obtained by intersecting a plane with a cone. Well, that is something that doesn't happen here, it happens here in a, what people sometimes call a degenerated fashion, because the intersection is just a single point. We will also talk about the pretty conic sections, the ellipses and hyperbolas and all those other things explicitly later on in another presentation. And so we're done with this part. Now, we've thrown a lot of stuff at you here, and there's a lot of stuff that you need to put into your brain, namely the connection between the equations and the two-dimensional curves or the three-dimensional curves, and also the beginning of visualization of three-dimensional surfaces. The computations themselves, they can be tedious, as we have seen in the completion of the square, but we can also acknowledge there was nothing new there. We know how to complete the square, so this computation, even if it takes a while, even if it is tedious, should have gone reasonably well. Alright, so you've got homeworks now. You've got homeworks on intersections, on recognizing shapes, and so on and so on. I'll leave you to that. You may also just want to take a break if you're as tired as I am right now. And so I'll leave that decision to you. We're going to continue talking about lines, which will be the next presentation, but I recommend you first work a lot on the subject of this one. So I'll see you whenever.